In computer networks, reference models give a conceptual framework that standardizes communication between heterogeneous networks. The two popular reference models are OSI model and TCP/IP protocol suite. This presentation covers these reference models in detail. The topics of discussion in this presentation are as follows. Firstly, we will appreciate the need for a protocol architecture. Then, we will discuss in detail about the two frequently used reference models, which are TCP/IP and OSI. The presentation will conclude by presenting about some of the applications and transmissions, and of course, you will be given some review questions for you to self-reflect what you have learned in this session. The need for standards and protocols can be explained simply. Just imagine what happens when people communicate in different languages. It is good if the sender and the receiver speak in the same language or to have an interpreter who can understand both languages. Over the past couple of decades, many of the networks that were built used different hardware and software implementations. As a result, they were highly heterogeneous and they were incompatible, and it became difficult for networks using different specifications to interact with each other. The ISO recognized there was a need to create a network model that would help vendors create interoperable network implementations. And that's where a reference model was introduced. So a reference model is established with the primary aim of promoting the standardization of network. Please note that the OSI is a conceptual framework that describes the functions of networking. OSI or Open System Interconnection Model was developed by International Standards Organization. It gives a layered networking framework that conceptualizes how communication should be done between heterogeneous systems. It has 7 interconnected layers. The 7 layers of the OSI model are physical layer, data link layer, network layer, transport layer, session layer, presentation layer, and application layer. The hierarchy is depicted in the figure. The Open Systems Interconnection Model (OSI model) is a conceptual model that characterizes and standardizes the communication functions of a telecommunication or computing system without regard to its underlying internal structure and technology. Its goal is the interoperability of diverse communication systems with standard communication protocols. The model partitions the flow of data in a communication system into 7 abstraction layers. From the physical implementation of transmitting bits across the communications medium to the highest level representation of data of a distributed application. Each intermediate layer serves a class of functionality to the layer above it and is served by the layer below it. Classes of functionality are realized in software by standardized communication protocols. For example, can you write a letter in a web browser? If you need to do banking, you have to do it in their corresponding banking application. So these are some of the examples that actually substantiates the need for these communication protocols. Communication protocols enable an entity in one host to interact with the corresponding entity at the same layer in another host. Service definitions like the OSI model abstractly describe the functionality provided to an n layer by an n-1 layer, where n is one of the 7 layers of the protocols operating in the local host. At each level, entities at the communicating devices exchange protocol data units. By means of a layer n protocol, each PDU, which is the protocol data unit, contains a payload called the service data unit, along with the protocol related headers or footers. The physical layer deals with the transmission of individual bits from one node to another over a physical medium. It states the data transmission rate, that is, the number of bits transmitted per second, and the duration of a bit, so how long a bit stays. At the bottom of our OSI layer, we have the physical layer, which represents the electrical and physical representation of the system. This can include everything from a cable type, radio frequency link, as well as the layout of pins, voltages, and other physical requirements. When a networking problem occurs, many networking professionals go right to the physical layer to check that all of the cables are properly connected and that the power plug hasn't been pulled off from the router, switch, or computer. In the data link layer, the stream of bits are split into data frames having sizes from a few hundred to a few thousand bytes. The data link layer ensures flow control of transmission so that a fast sender does not drown a slow receiver. In case of reliable connection, this layer ensures that the receiver sends an acknowledgement frame. In absence of acknowledgement frames, frame retransmission is done. It also has mechanisms to identify duplicate frames. The data link layer provides a node-to-node data transfer, that is between two directly connected nodes, and it also handles error correction from the physical layer. Two sublayers exist here as well, the media access control layer and the logical link control layer. In networking, most switches operate at layer 2, but it's not that simple. Some switches also operate at layer 3 in order to support virtual LANs that may span more than one switch subnet, which requires routing capabilities. The data link layer is responsible for reliable node-to-node delivery of the data. It accepts packets from the network layer and forms frames and gives it to the physical layer as shown. The data link layer is responsible for moving frames from one hop to the next. So the figure illustrates that the communication at data link layer takes place between two adjacent nodes. The data is being sent from end system A to end system F. To do so, three partial deliveries are made. First, the data link layer of one sends a frame to the data link layer of the B router. Then the data link layer of B sends a new frame to that of E, again a router, and finally the data link layer of E send a new frame to the data link layer of the end system F. The network layer controls the source to destination delivery of data packets across multiple hops. It controls the operation of the subnet. The routes can be based upon static tables that are rarely changed, and they can be automatically updated depending upon network conditions. Jitter is a familiar term that can be used to cover a range of problems relating to timing in electronic circuits. Here at the network layer is where you will find most of the router functionality that most networking professionals care about. In its most basic sense, this layer is responsible for packet forwarding, including routing through different routers. You might know that your computer wants to connect to a server in a different place, but there are millions of different paths to take. Routers at this layer help to do this efficiently. The main function of this layer is to deliver packets from source to destination across multiple networks. If two systems are connected on the same link, there is no need for a network layer. The relationship of the network layer to the data link layer and transport layer is clearly shown in this image. As shown in the image, we are expected to make a source to destination, that is end-to-end delivery. The sequence of events takes place as follows. At first, network layer of end system A sends the packet to the network layer of the intermediate system B, which is a router. The router B makes a decision based on the final destination of the packet. This router uses its routing table to find that the next hop is the router. The network layer of B sends packet to the network of router E. The network layer of E will then send the packet to the network layer of the end system F. The transport layer is responsible for delivery of an entire message from an application program on the source device to a similar application program on the destination device. It delivers a message from a specific process of one computer to a specific process in another computer. It identifies errors like damaged packets, lost packets, and duplication of packets, and provides adequate error correction techniques. A port number is the logical address of each application or process that uses a network or the internet to communicate, as allocated by the operating system. The transport layer deals with the coordination of the data transfer between end systems and hosts. How much data to send, at what rate, and where it goes, etc. are dealt by transport layer. It accepts data from above, split into smaller units as needed. Multiplex multiple connection over a single channel is also done in this layer. The best known example of the transport layer is the Transmission Control Protocol (TCP), which is built on the top of the Internet Protocol (IP), commonly known as TCP/IP. TCP and UDP port numbers work at layer 4, while IP addresses work at layer 3, the network layer. The transport layer is responsible for process-to-process delivery, the delivery of a packet, part of a message from one process to another. Just to reiterate, the data link layer is responsible for delivery of frames between two neighboring nodes over a link. This is called node-to-node delivery. Transport layer is responsible for process-to-process delivery of entire message, whereas network layer oversees host-to-host delivery of individual packets across multiple links. The session layer, it can be compared as a telephone operator that connects two parties over the telephone. When two devices, computers or servers, need to speak with one another, a session needs to be created, and this is done at the session layer. Functions at this layer involve setup, coordination, and termination between the applications at each end of the system. Session layer is the layer of the ISO open systems interconnection model that controls the dialogues between computers. It establishes, manages, and terminates the connections between the local and remote application. The session layer is responsible for establishing, managing, synchronizing, and terminating sessions between the end user application processes. It works as a dialog controller. It allows the system to communicate in either half duplex or full duplex mode of communication. It is responsible for token management. The presentation layer represents the area that is independent of data representation at the application layer. In general, it represents the preparation or translation of application format to network format, or from network formatting to the application format. In other words, the layer presents a data for the application or the network. A good example of this is encryption and decryption of data for secure transmission. This happens at layer 6. In the OSI model, the presentation layer ensures the information that the application layer of one system sends out is readable by the application layer of another system. If required, the presentation layer might be able to translate between multiple data formats by using a common format. The application layer is one of the top. It is what most users see. In the OSI model, this is the layer that is the closest to the end user. It receives information directly from users and displays incoming data to the user. Oddly enough, applications themselves do not reside at the application layer. Instead, the layer facilitates communication through lower layers in order to establish connections with applications at the other end. Web browsers, for example, your Google Chrome, Firefox, Safari, etc., Telnet, and FTP are examples of communications that rely on layer 7. This layer is used for applications specially written to run over the network. The application layer is responsible for providing services to the user. The presentation layer receives the data from the application layer and translates it into a format and syntax that's readable by other computers. In order for other systems to recognize this data, it is converted into a generic format that is not application specific. Data encapsulation is a process in which some extra information is added to the data item to add some features to it. We use either the OSI or the TCP/IP model in our network, and the data transmission takes place through various layers in these models. The packet is the basic unit of information transferred across a network, consisting at a minimum of a header with a sending and receiving host address, and a body with the data to be transferred. As the packet travels through the TCP/IP protocol stack, the protocols at each layer either add or remove fields from the basic header. When a protocol on the sending host adds data to the packet header, the process is called data encapsulation. Moreover, each layer has a different term for the altered packet, as you can see in the image. The packet's history begins when the user on one host sends a message or issues a command that must access a remote host. The application protocol associated with the command or message formats the packet so that it can handle by the appropriate transport layer protocol TCP or UDP. When the data arrives at the transport layer, the protocols at the layer start the process of data encapsulation. The end result depends on whether TCP or UDP has handled the information. Both TCP and UDP pass their segments and packets down to the internet layer where they are handled by the IP protocol. IP prepares them for delivery by formatting them into units called IP datagrams. IP then determines the IP addresses for the datagrams so they can be delivered effectively to the receiving host. P attaches an IP header to the segment or packet's header in addition to the information added by TCP or UDP. Information in the IP header includes the IP addresses of the sending and receiving host, datagram length, datagram sequence order. This information is provided in case of the datagram exceeds the allowable byte size for network packets and must be fragmented. Data link layer protocols such as PPP format the IP datagram into a frame. They attach a third header and a footer to frame the datagram. The frame header includes a cyclic redundancy check field that checks for errors as the frame travels over a network media. Then the data link layer passes the frame to the physical layer. The physical network layer on sending host receives the frames and converts the IP addresses into the hardware addresses appropriate to the network media. The physical network layer then sends the frame out over the network media. When the packet arrives on the receiving host, it travels through the layers in the reverse order from that which it took on the sender. Moreover, each protocol on the receiving host strips off header information attached to the packet by its peer on the sending host. Here is it what happens. Physical network layer receives the packet in its frame form. It computes the CRC of the packet, then sends the frame to the data link layer. The data link layer verifies the CRC for the frame is correct and strips off the frame header and CRC. Finally, the data link protocol sends the frame to the internet layer. The network layer reads information in the header to identify the transmission and determine if it is a fragment. If the transmission was fragmented, IP reassembles the fragments into the original datagram. It then strips off the IP header and passes the datagram onto the transport layer protocols. The transport layer reads the header to determine when application layer protocol must receive the data. Then TCP, IP and UDP strips off its related header and sends the message or stream up to the receiving application. Application layer receives the message and performs the operation requested by sending host. This is more similar to OSI model. The TCP/IP protocol suite is a collection of protocols that are used in the internet. It is named after the two main protocols, TCP and IP, and uses a four-layer networking model. Just to reiterate, the TCP/IP protocol suite is named from the two of the most important protocols in it, the Transmission Control Protocol and the Internet Protocol, which were the first two networking protocols defined in the standard. The two main protocols in the IP suite serve specific functions. TCP defines how applications can create channels of communication across a network. and this is very flexible and robust. Now it's time to compare both the reference model that we have learned till now. Let's start by addressing the similarities that both of these models have. Following are some similarities between OSI reference model and TCP IP reference model. The first one, both have layered architecture. The layers provide similar functionalities, and both are protocol stack, and both are reference models. Some of the differences that could be highlighted are OSI has 7 layers whereas TCP/IP has 4 layers. The OSI model is a logical and conceptual model that defines network communication used by systems open to interconnection and communication with other systems. On the other hand, TCP/IP helps you to determine how specific computers should be connected to the internet and how you can be transmitted between them. OSI header is 5 bytes whereas TCP/IP header size is 20 bytes. OSI refers to the open systems interconnection whereas TCP/IP refers to transmission control protocol. OSI follows a vertical approach whereas TCP/IP follows a horizontal approach. OSI model, the transport layer is only connection oriented whereas the TCP/IP model is both connection oriented and connectionless. OSI model is developed by ISO, whereas TCP model is developed by ARPANET. OSI model helps you to standardize router, switch, motherboard, and other hardware, whereas TCP/IP helps you to establish a connection between two different types of computers. The difference between the TCP/IP and the OSI model is tabulated and is clearly shown in this slide. So basically this table presents the difference between these two models and you can use this for your reference. Now let us try to understand the TCP/IP network architecture in detail. The OSI model we just looked at is just a reference or logical model. It was designed to describe the functions of the communication system by dividing the communication procedure into smaller and simpler components. But when we talk about the TCP/IP model, it was designed and developed by the Department of Defense in 1960s and is based on standard protocols. It stands for Transmission Control Protocol, Internet Protocol. The TCP/IP model is a concise version of the OSI model. It contains 4 layers, unlike the 7 layers in the OSI model. The layers are process or application layer, host to host or transport layer, internet layer, network access or link layer. The transmission control protocol and the internet protocol are combined together as TCP/IP. These protocols describe how data on the internet is packaged, addressed, sent and received. TCP/IP uses the client-server model of communication in which a user or a machine is provided a service like sending a web page by another computer in the network. Collectively, the TCP/IP suite of protocols is classified as stateless, which means each client request is considered new because it is unrelated to the previous request. Being stateless frees up network paths so that they can be used continuously. The transport layer itself, however, is stateful. It transmits a single message and its connection remains in place until all the packets in a message have been received and reassembled at the destination. The TCP/IP model differs slightly from the 7-layer OSI model designed after it. The OSI reference model defines how applications can communicate over network. The TCP/IP specifications described a lot of applications that were at the top of the protocol stack. Some of them were Telnet, FTP, SMTP, DNS, etc. File transfer protocol is reliable, simple, and efficient, and it allows peer entities to carry conversation. The transport layer decides if data transmission should be on parallel path or single path. Functions such as multiplexing, segmenting, or splitting on the data is done by transport layer. Transport layer adds header information to the data. Transport layer breaks the message into small units so that they are handled more efficiently by the network layer. Transport layer also arrange the packets to be sent in sequence. Network layer is the layer which holds the whole architecture together. It helps the packet to travel independently to the destination. The movement of data means routing of data over the network. The link layer is also known as the network interface layer. This layer normally consists of device drivers in the operating system and the network interface card attached to the system. Both the device drivers and the network interface card take care of the communication details, with the media being used to transfer the data over the network. In most of the cases, this media is in the form of cables. Just to emphasize and for you to understand and appreciate the differences between OSI model and TCP IP model, the tabulation which has the difference between these two models is presented over in this slide. Now let us do this discussion forum activity. The forum has already been created and you should be able to post your response by creating the thread in the respective forum. So the questions are listed above in this projection. I want you to post the answers for these questions shown above in the discussion forum by creating the thread, and I want you to do this as quickly as possible. We have come to an end of this session. Thank you for listening. Should you have any queries, please do write to me or let me know during the session. After completing the activity, you may leave. See you in the next session.